So today I'll be covering two things. The first thing is your mirror image, is the okay, is your method of mirror image or image charges. And the second is on using separation of variables to solve Laplace equations. Okay, and just as a broad overview, image charges is a very niche kind of trick that you can use to do problem solving. And it's basically, if this comes out in the competition and you know how to do it, it's free marks lah. I think my senior year, Jin Hing's year, their last question is a 10-mark question just on image charges. So actually, if you don't know too much about this, it doesn't really matter. When it comes to solving Laplace equations using separation of variables, this is actually a completely bonus thing lah. So, but for the sake of completion, I'll cover it over here. Okay. So to begin with, what exactly do we mean by an image charge? And I will do this with an example of a question. So basically, we have an infinite grounded plate. Okay, this is an infinite grounded plate. So we imagine that this plate moves out in the x and y y-axis. And let's just say we bring in a charge, some positive charge, or let's just call some charge q at some position 0, 0d. Okay, and what is going to happen, or what is this charge going to do to the grounded plate, is that it is going to induce the pencil is a little bit difficult to see, huh? Okay. It is going to induce some surface charge over here. Okay, and because of this surface charge, we're going to expect some sort of attraction between Q and the plate. Is that correct? Okay. And now the question that we want to ask, right, is basically, yeah, what is the potential everywhere in the region outside of this plate, and what is the force between Q and our plate? And in order for us to do this question, right, well, one way that we can think about how to approach this question is that we can assume that sigma takes along some function of xy, is some function of xy along this plate. And then what we can do is we can write our potential everywhere, and to find a appropriate function sigma such that everything here is equal to 0. Okay, such that everything along this plate is equal to 0, and when you're at infinity, your answer is equal to 0. And this is one approach that you can go about doing the problem. In fact, this is basically what problem 5.5.1 is asking you to do. But the thing is, we can cheat this. We can cheat this by simplifying it and not actually having to find the explicit charge distribution. And the way that we do this is that we know what the value of potential is at this boundary. So we know that v is equal to 0 when z is equal to 0. And we also know that v will approach 0 when z becomes, or when your distance from the center becomes very, very large. Okay, and this basically tells us that we know v on all boundaries. Okay, so since we know v on all boundaries, right, we can apply our uniqueness argument to tell us that there is only one possible. Okay, so there is only one. There is only one function v x y z that satisfies these properties. Okay, and since there is only one function, right, all we need to do is we need to find some suitable charge distribution that allows us to satisfy these conditions. And if you were to remove this grounded plate completely, right, and you consider a situation where you have a Q at 0, 0d, and you have a minus Q at 0, 0 minus d, then by symmetry, we know that on this plane in between, right, V is going to be equal to 0. And everywhere outside, as the further and further away you go from from this charge distribution, you're going to expect V to fall to 0 as well. So this particular charge distribution satisfies our condition. So what we can say, right, is that the potential V in this region on top is going to be the same as the potential V here. Okay. And because of this, we can explicitly write down the potential immediately. It is just going to be equal to 1 over 4 pi epsilon naught. Da, 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 da. Okay, so this is the distance from the positive charge, and this is the distance from the image charge. Okay, so as simple as that. And in general, if you are given a problem with a grounded conductor, if there is a symmetry in the problem, your first thing that you should think of, it should be what image charge can I introduce in order to satisfy the boundary conditions. Okay, but there are a few rules for applying mirror charges lah. And the first biggest rule, right, is that you cannot put a mirror charge in the region that you're interested in. Because by putting a mirror charge where you're interested in, you have basically changed the equations within this region. So for instance, if I have this situation on top, right, I cannot say put some charge distribution of minus q's a bunch over here, such that it satisfies the boundary condition. Okay, I can't put a random distribution minus q that satisfies the boundary conditions and say that, okay, this generates the correct V. That cannot be done. So again, your mirror charge can only be put in places where you are not interested in. Okay. And after you have found V, if you want to find the electric field or if you want to find the charge density, you just apply the formulas as before. Okay. So just as a demonstration, right, your sigma will just be equal to minus epsilon naught partial V partial Z. Z is equal to 0. Okay. And you can plug this in here and you can get your answer. Just going to write it out over here. Okay, and as you expect, the sign of the induced mirror charge is going to be opposite from your charge that you have introduced. So the minus q there is consistent. And if you were to integrate this charge density over the entire plane, you're going to get the value minus q. So it will be your induced charge, the total induced charge is going to be exactly the same as your charge here. Okay, the force between the conductor and the charge is simply just going to be your Coulomb's force between the two mirror charges. And the logic is very simple. It's because whatever V that your minus Q produced, right, is going to be the same V that your surface plate produced. So the electric field produced by this is going to be the same as that of the minus Q. So the force between the two, you can just write down using Coulomb's law. So it will be, okay. The only difference, or the only thing that you cannot directly translate from mirror charge to the physical world is the potential energy. So the potential energy of this setup, right, is not going to be equal to your QQ over R. And the reason why is because you imagine what happens when you bring in a charge Q from very far away. There will be charge that will enter due to okay, so it will induce some charge on the surface here, right? But the charge on the surface here is not actually brought in by you. It is brought in by the potential source over here. It is brought in by the potential source over here. So you do no work in bringing in the rest of the charges. You only do work when you bring in Q. So there are two ways to actually find potential energy. The first way is you can invoke a symmetry argument. Okay, and the symmetry argument is very simple. It basically says that your field on top and below is symmetrical. And because your field is symmetrical, right, and your energy is going to be epsilon naught over 2 integrating your E squared, this lah. Then if you only consider half of it, because the bottom half is a conductor, the electric field here will be 0. So if you only consider half, right, then this integral over all volume is just going to be half of what you expect in your mirror charge situation. And this gives you the correct answer. But if you're not convinced by the symmetry argument, the alternative way you can do it is you can simply integrate the work. Because you know what the force is as a function of distance, if you just integrate the work from infinity to this point, yeah, you will get the correct answer as well. So the details of what I've said have been basically have been written out in the worksheet lah. So give it a careful read on. Okay, and apart from the conducting plane example, the most other common examples that you will see will be either a conducting sphere or a conducting cylinder. Because once the geometry becomes difficult, right, it becomes very difficult to introduce proper mirror charges that satisfy the boundary conditions lah. Okay, I think I will let you guys work on the problem in your own time. So are there any questions on this small topic on mirror charges? Huh?
How did you find the boundary conditions in?
Okay, so the boundary conditions here is given by the question. The question tells you you have a charge Q and you have a infinite grounded plate. So from what you can imagine, right, if the plate is grounded, then you will expect the potential at the bottom to be equal to 0. And the second boundary condition is that if you're very, very far away from this charge distribution, you expect V to be 0 as well. And that also makes sense lah. Yeah, so in general, right, depending on the situation, you're going to have different boundary conditions. So for instance, if you were to have a situation where you have a conducting sphere or a grounded sphere and a charge Q, then your boundary condition will be V is equal to constant on the surface of the sphere and V approach 0. Okay, V is equal to 0 on the surface of the sphere. And V approach 0 as your distance R approaches infinity. So these will be your two boundary conditions. Okay, any other questions with regards to mirror charges? Okay, if not, I'm going to move on. And I'm going to move on to separation of variables. And this is something that I presume most of you have not touched on before. So just as a context of what level this entire topic is, I think this is quite standard in your year 1 university. If you do physics as a year 1 student, year 1 undergrad. And before we actually go on to what exactly is separation of variables, we have to understand something called the Fourier series. Okay. And I'm going to introduce this not as a problem in electrostatics, but rather as a much simpler thing that you guys are all very familiar with, which is a vibrating string. So imagine I have a string that I have tied down at two ends. Okay, I have tied down at two ends, and I let this string vibrate. Okay. Well, we know from our physics knowledge that you're going to form a first harmonic. You can form a first harmonic. You can form a second harmonic. You can form a third harmonic, right? And the question now that we want to ask is, if I were to pull this string in some random direction, so let's just say I were to start off this string in some funny pattern that looks like this, how will it develop with time? Okay, how will this pattern develop with time? And this specific question actually has an explicit answer with reference to the shape of this. But we're not particularly interested in this way of solving it. Instead, we are more interested in using the Fourier series to solve it. And let us first think about what we're actually trying to solve, okay? And the problem that we're actually trying to solve is actually the wave equation in one dimension. So it is going to, let's just imagine that we call this our x, and at each point there is a certain height to this string. There is a certain y of x to this string. Then the equation that this string satisfies, and this can be shown using your Newton's law, is that is going to be some constant times this. Okay. And let us just, for the sake of convenience, let's just throw away this constant. We're just going to assume that it's going to be proportional. And again, let us make a few more simplifications. We are going to make this string extend from 0 to pi. And the first thing that I want to show you guys is basically, let us just try guess a solution. One of the most commonsensical solution is, because we understand that the string will form harmonics, is to simply guess a solution where your answer is a harmonic. For instance, sine x times cosine t. Okay. And let us actually plug this into this equation. Okay, y is equal to sine x times cosine t. Let us plug this into this equation. So on the first part, our partial y partial x is going to give us sine becomes cosine, cosine becomes minus sine. So this is going to give us sine becomes cosine, cosine becomes minus sine. Minus sine x cosine t, right? And on the other hand, our derivative with respect to t is going to give us cosine gives us minus sine, and minus sine gives us cosine. So this is going to give us this. Okay, so these two are equivalent. And because these two are equivalent, we do know that this is a possible solution. So this is a possible solution. And the fact that this is a possible solution shouldn't surprise you, because if you think about it, what sine x is saying is basically you have a graph that looks like this. It goes as a sine from 0 to pi, and the cosine t part is just your vibration of this string going up and down, up and down, up and down, right? And if you think about it, sine 2x cosine 2t is also a possible solution, okay? Is also a possible solution. And this will just correspond to your second harmonic. In fact, you can show that all of your solutions of this form do indeed satisfy your wave equation, okay? They all satisfy your wave equation. So the question is, if we were to be given an arbitrary shape to begin with, right? And we know that, okay, and we know that, let's just say this is a solution and this is a solution. We can simply add in together any linear combination of solutions and we still get a solution. You can verify this for yourself. What we basically want to show is that if we have some shape, why not? Some shape, why not? We want to be able to write this as a sum of some, let's say, a1 sine x cos t plus some constant sine 2x cos 2t, etc., etc., etc. And the moment that we are able to do this, right, the moment that we are able to find all of these constants such that this is true, right, we have basically solved the problem. Okay, we have basically solved the problem. So there are a few. Okay, so the cosine t here should be a 1 because you're interested at time t is equal to 0. Okay, so we're interested. So y here is the shape at t equal to 0. Everyone still following with the argument? Okay. And yeah, and basically this is the idea of your Fourier series. You're basically taking a specific graph and you're decomposing it into your sines and your cosines. And for the most part, before the convergence was proven, right? And for the most part, most people thought that this was just a simple mathematical amusement kind of thing, because their understanding of a function is that if you were to have something that looks like this, right, you will either have to break this up into two separate parts, or you to have a function with a discontinuity. And the understanding is that if you have a collection of sines and cosines and you add them together, there is no way in hell that it is going to converge into something that looks like this. Okay. And basically, what happened was Fourier, he did a lot of his experimental work on heat conduction, and what he did show was that there is a very, very good experimental fit between his prediction from his series, from the series, to the actual data. And this kind of shifted the point of view. Instead of thinking of this as an amusement, there became more effort into proving that the convergence is actually true. But it wasn't until I think the 18 somethings where Dirichlet formally managed to prove the convergence. And what he proved was actually particularly powerful in a sense that if you were to have a graph, and as long as this graph has a finite number of discontinuities, if it has a finite number of discontinuities, its Fourier series will converge to the graph at every point, and at any discontinuity, it will converge to the point in the center. Okay, and because of how easily this series converges, right, it is actually a very, very useful series in a lot of different situations. Because yeah, in physics, you don't expect things to have an infinite number of discontinuities. Okay, so how do we actually find the coefficients of the Fourier series? That is a very interesting question, and we're going to look at it now. And the way that we're going to think about this is I'm going to talk about this particular integration. Okay, and let us not think about why we talk about this integration first. Let us actually try do the integration, and I'm going to give you guys a few tricks on how to do this, how to remember these formulas. So the first thing that we want to start off always is our compound angle. So if you guys don't remember this off the bat, and I really don't remember this off the bat, I always derive it on the spot. But basically, if you have a sine a plus b, okay, you think about your double angle. Your double angle gives you 2 sine theta cosine theta, right? So you're going to expect this to be a sine A cosine B plus sine B cosine A. Likewise, your cosine A plus B, if you think of a double angle, this gives you a cos square minus a sine square, right? So you're going to expect this to be a cos A cos B minus a sine B. Okay. So at this point in time, the sine A sine B is over here. So what we want to do is we want to find a way of getting rid of this. Okay. And the way we do this is we have to exploit some of the evenness and oddness of what is going on. So cosine A minus B is going to be equal to cos A cos minus B minus sine A sine B, right? And when your sine minus B, okay, and when your sine is changes sign, it changes sign outside. If your cosine changes sign, it doesn't change outside. So this gives you cos A cos B plus sine A sine B. Okay, and yeah, this is basically it. So what we get from here is that this is going to be equal to half of cos nx minus mx minus cos nx plus mx. Okay, and whenever you're integrating a cosine from minus pi to pi, you're going to end up with some sine, right? And if you end up with a sine pi, sine minus pi, no matter what integer multiple, right, you're going to get the answer of 0. So this is always going to be equal to 0, except for this one very particular situation, right, where your first term is not a cosine. So in other words, when n is equal to m, this is not equal to 0. Okay? When n is equal to m, this is not equal to 0. In all other situations, this is going to be equal to 0. And so let's just say we have some function f of x, and let's let this function range from minus pi to pi. And if we presume that it can be written as a sum of sines, what you can simply do, right, is you can, let's just say we're interested in the nth term. You can simply multiply both sides by sine of nx. And the only non-zero term in the right-hand side of this equation is going to be this term, okay? It is going to be this term. And the specific value of this is going to be, looks like 1 over, so this becomes a half, it's going to be equals to pi times an, right? So this is the basic idea behind the Fourier series, and this particular property, right? This particular property over here is what we call orthogonality. Okay, and this is something that you're going to see a lot once you start learning all your linear algebra nonsense and whatever. It's going to be an important thing, and it doesn't just apply for the sines. It applies for both the sines and the cosines. So basically, sine. Basically, this is always going to be equal to 0, and this is going to be 0 if n not equals to m, and pi if n equals to m. I feel like it's not supposed to be pi. One. Okay. Yeah, and now we can start actually applying this into our Laplace equations. Okay. Okay, the separation of variable comes in now. Okay. So basically, let us imagine that we are given a system that consists of two grounded plates. Okay, so the first grounded plate is your xy plane. So this is the top grounded plate and the bottom grounded plate, and there is a narrow band over here. There is a narrow band over here. Okay, and this narrow band has some potential v naught of y. And the question that we want to ask now, right, is what is the potential inside this entire strip? And because this has no dependency on, like, there is the symmetry of the argument means that there is no partial v partial y term, right? Okay, I've labeled this slightly different in my worksheet. I'll just follow that. Okay. So there is no partial v partial y term in this particular case. Partial z, yeah, partial. Oh yeah, because the plane extends this way, so there is no change when you move along the z-axis. So your partial v partial z term is 0. You're basically solving this particular set of equations. Okay, with the given boundary conditions, v is equal to 0 when y is equal to 0, v is equal to 0 when y is equal to a, v is equal to v naught when x is equal to 0, and v becomes 0 as your distance becomes infinity. Okay, and all of these, okay, the first two, okay, the first three are basically statements from the question. The third one is basically just use your physical intuition. And our understanding right now is that there is only one possible solution, because we know that the uniqueness must hold. And so we don't need to bother proving that there is only one solution. We know for sure. And that means as long as we find a single solution that satisfies all of these boundary conditions, we are done with the problem. And this is where separation of variables comes in. It's basically helping us to construct a possible solution. Okay, and the way we're going to do this is we're going to assume that your potential is going to be two separate functions that are completely independent of each other multiplied together. Okay, and this may seem like a kind of silly expectation, because if you think about it, a large majority of your solutions do not satisfy this condition. If, for instance, 5x plus 6y is a solution that satisfies your Laplace equation, but it doesn't fit into the criteria over here. And it seems like if we make this assumption, we are losing out on a lot of possible solutions. But in a moment, we will show why taking a solution like this is sufficient. Okay, and if we were to simply just plug this into our Laplace equation, we're going to get, okay, this is going to be equal to, okay, we're going to get this. And if I were to shift the x, all of the x on one side and all of the y on one side, And basically, this is why the name why it is called separation of variables. Variables are you're basically separating the variables by what they are dependent on. And if you take a look at this equation, right, this over here is a function of x. So this is a function of x. This is a function of y. So if a function of x is equal to a function of y everywhere, then the only thing that can satisfy both equations at once is this must be equal to a constant. Okay, this must be equal to a constant. Okay, so what is the value of this constant? This constant we can largely partition into three separate cases. So it can be positive, it can be zero, it can be negative. And at this point in time, you guys should already be quite familiar with your second order linear differential equations. But basically, if you have an equation that looks like this, y prime plus cy is equal to 0. If this is positive, you get a sine plus cosine kind of solution. If it is 0, then you will get a linear solution. And if it is negative, you will get a e to the x plus e to the minus x solution. Is that correct? And so at this point in time, all we need to do is we need to think about what is happening within our, like, which of these are allowable solutions given the boundaries of our question. And if you think about it, the most obvious thing is that if your is that okay? If you take a look at this from the side point of view, and this is your y, right? Everything here must be 0. Everything here must be 0. So if we were to take a look at the solution from the y point of view, right? Well, obviously this cannot be a linear. This cannot be a sum of some exponential because it will have to cross the 0 line twice. So this must be some combination of sines or cosines. So from this equation, we do know that we are going to expect c to be a positive number. In particular, we're going to expect this equation, we are going to expect this thing to be positive. Okay, we're going to expect this thing to be positive. So at this point, we can let c be equal to some k squared. Okay, and so we have a general solution already. Our x is going to be equal to some kx plus, and our y is going to be equal to some sine plus some cosine, right? And at this point in time, what we need to do is we need to actually fit in the values of our boundaries. And the most convenient boundary, once again, is the one that is 0 here and 0 here. And this basically means, right, that we're going to expect this to be a sine. It's going to be a sine that is going to start from here and is going to end from there. Or more conveniently, we can write our second solution here simply to be as some c sine n pi over a times y, where our n belongs to big N. Okay. And the second thing that we know, right, is that okay, our v is going to become very small once x becomes very large. So this exponential term here cannot exist. You see, because if this exponential term here exists, it implies that your v must become infinity once your distance becomes infinity. So we can throw it away, and basically we can write our solution. V is equals to the sum of some sets of constants Cm e to the minus okay, it's going to look something like this. Okay. And how do we find the appropriate constant Cm? This is where the Fourier series comes in, because we do know that v is equal to some function when x is equal to 0. Or in other words, we know that v naught y is going to be equal to and so what do we do? We multiply both sides by sine n pi over a, and we integrate from and on the right hand side, okay, on the right hand side, this integration is going to remove all of your terms where where the coefficient here is not equals to n. So this is just going to be Cn times a over 2. And so this gives us our final expression for Cn. Oh, forgot the dy. Cn is going to be equal to 2 over a times this integration. And so we can finally put all of this in together, and we are able to get a general solution. So the general solution of what the potential is going to look like inside is going to be this. V is going to be equal to with Cn defined as this. Okay, so far so good. Okay, I think a lot of this, a lot of the difficulty in doing this is not really in the math. If you do more of the questions, you'll get a better feel of what is going on. Some of these things, honestly, it's better to just derive on the spot than to blindly memorize the formulas, lah. Okay. So let me just give a short recap. When it comes to the separation of variables, what you want to do is you want to assume that your v is going to be equal to some function of x, some function of y, some function of z. This is in Cartesian coordinates. And once you are done, when you do the differentiation, you are going to end up with something that looks like this: x, y, dz, dz, plus blah, blah, blah. And at this point, you divide by 1 x, y, z to get 1 over z And at this point in time, you know this is a function of z, this is a function of x, this is a function of y. And if they sum to 0, it must mean that they are all constants, c1, c2, c3, with the sum c1 plus c2 plus c3 equals to 0. Once you're done with this process, you fit the boundary conditions to find out the signs of your individual c1s, the signs of your different constants, okay? And once you're done with the signs of the constants, the last step is you want to use your Fourier trick to find the coefficients of your of the terms in your equation. Okay. So again, I suggest you guys try the problems if you want to get a better feel of what is actually going on. Because sometimes going through the math it's very difficult to to explain the math if you don't actually try and do the problems. Okay. So this is the separation of variables in Cartesian coordinates. The second part of this problem is about separation of variables in spherical coordinates. Okay, and the separation of variables in spherical coordinates is generally a little bit more complicated because your Laplace equation reads much more complicatedly in the spherical coordinates. It's going to look like this. Okay. Okay, and just a interesting thing to note is that when people talk about what a harmonic is, right? A harmonic is basically a solution to a Laplace equation. Okay, so if you guys ever hear the word harmonic, keep in mind that that is referring to a solution to a Laplace equation. Okay, and in this particular worksheet, right, I'm not actually going to go through with you the cylindrical dependency because if there is a cylindrical asymmetry, right, you're going to end up with a lot of different Bessel functions. So I think for the sake of complexity, this is a bit too much, lah. This is a bit too much. But your r and your theta dependency we solve in a very similar way to our Cartesian coordinates. So once again, we can simply assume v is going to be equals to rr times some theta theta. Okay. And if we were to throw this into the Laplace equation, we are going to get something that looks like this. Okay. And once again, we invoke the same logic. This term is nothing but r's. The first term is nothing but r's. The second term is nothing but theta. So in order for their sum to be a constant, right, this must be a constant C1, and this must be a constant minus C1. Actually, because there are only two, no need for the subscript lah. Okay, and the first equation, once you expand it out, you will get something that looks like you'll get something that looks like this. Okay, so actually, let me just copy it over. So your radial equation is going to look like this. And this is, if you guys are familiar, is what we call a Cauchy-Euler equation. But I think the more sensible name is, this is called the Euler equidimensional equation. And the reason why we say this is because if you take a look at the powers of r in this equation, right? Here we have an r square, here we have an r, and here we have nothing. And so if you think about what happens when we differentiate r to the n, right? R to the n becomes what? N r to the n minus 1, followed by n minus 1, Rn minus 2. So if we were to make the substitution, r is equal to some r to the n, right? What is going to happen is that your Rn n minus 2 and r square is going to combine to give you a Rn. So these two are going to combine to give you an Rn, and basically you can throw away Rn from the equation completely. Okay, you can throw away Rn from the equation completely, and this lets you solve the equation on top as some quadratic equation. And the reason why we choose to let the constant c be equals to L times L plus 1, right? This is part of the reason, okay? Because if you use this particular form, you end up with very nice solutions, okay? In particular, the solution is going to look like this. R of r is going to look like a r to the L plus b over r L plus 1. So this is your radial equation. Your angular equation is going to be actually quite a bit more complicated. And it is going to look like this. Okay, and at this point in time, you can do the substitution cosine theta is equal to x. And what you do get is you end up with an equation that looks like this. Okay. And if you want to solve this equation, what you can do is you can assume that theta takes the form of some a0 plus a0x plus a1x plus a2x squared, and you solve explicitly for your individual coefficients. Okay. And once you eventually do this, you're going to realize that most of your solutions to this equation is going to blow up to infinity. Okay. In fact, the only solutions that do not blow up to infinity is if your L over here is going to be equal to some integer number, so 0, 1, 2. And the particular polynomials defined by these integer numbers, right, are what we call the Legendre polynomials. Okay, and this is also something that if you have read up above and beyond in your linear algebra and whatever nonsense, you are going to see this term pop up quite a bit. So I guess it's good as, I mean, no time like the present to get acquainted with it, right? And basically what we can do is that we can write the general solution Vr of theta to be equal to an expression that looks like this. Okay, and again, this expression looks a lot more scary than it actually is. It actually just says a lot of very simple things. Okay, and once again, the Legendre polynomials satisfy orthogonality, as in that they are a set of orthogonal functions, in the sense that if I were to do this integration, you're either going to get 0 if n is not equals to m, or 2/2n plus 1 if n is equal to m. Okay, and basically, if you want to find the coefficients AR and BL, typically you're going to have to make use of this orthogonality somewhere lah. Okay. Okay, again, I would say from the aspect of a competition point of view, this particular topic is not important at all. But when it comes to your uni education, right, this is going to be quite a big thing. So it is good to get acquainted with it early on lah. Okay. So again, a lot of this is about experience in solving problems. Once you start solving the problems, you understand that the theory really isn't all that scary. Okay. At this point in time, I basically covered all of the content that I want to cover. Again, the worksheet is quite a bit more detailed than what I've gone through by mouth, and I will recommend that you do most of the mirror image problems. The Laplace equation problems, try if you are confident enough with the mathematics. And I think I will just briefly go through a few common situations. Okay. Should I? Okay. So yeah, I think not necessary lah. You guys just try the problems by yourself, and if you need help with them, you can always ask me. But if not, I don't have much else for you guys this week lah. Yeah, I know you guys are busy with school, so I'll just dismiss you guys now lor. Okay.
Thank you.
Bye bye.
Bye bye.
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 Bye bye. Bye bye.